this is Joy. Today I'm going to show you how to use Multisim to calculate branch currents or solving network theorems. Now this is a basic problem of a simple T network of series arm impedances of 100 ohms, 180 ohms, and the shunt arm impedance is 150 ohms. I have taken a simple voltage of 12 volt DC and a load resistor of 75 ohms. Now if we simulate the circuit, uh, then we can find the circuit current to be 22.87 milliampere, 857 milliampere rather. Now we are going to use Thevenin's theorem in order to solve this problem. What is Thevenin's theorem? Thevenin's theorem is basically a simple network theorem which is used in networks for simplifying the circuit, and a very popular tool for solving complex networks problems. Now what we do in network theorem like Thevenin's theorem, we simply first disconnect the load, that is 75 ohms, that is RL here, and we have made this port open and measured voltage from here, that is as shown here, calculating the open circuit voltage, and it is called VOC or VTH, that is Thevenin's equivalent voltage, and we found it to be 7.2 volts. Now what is the next step? The next step is measuring the Thevenin's equivalent resistance, and this is the setup. What is the difference between this and this? That is, during measuring the Thevenin's equivalent resistance, we will not have any sort of source in the network. All sources will be made inoperative, that is, the voltage sources will be replaced by their internal resistances, or it is an idle voltage source, so we have shorted here. If it have been a current source, we would make this open circuited. What is the Thevenin's equivalent resistance we found? There is 240 ohms. Now what is the last step? The last step is drawing the Thevenin's equivalent circuit. What is this? The Thevenin's equivalent voltage VTH 7.2 volts here, in series with the Thevenin's equivalent resistance, that is 240 ohms here, and in series with the load resistance, and we will measure the current through this terminal, that is found to be 22.857, and that was exactly the same that we found in the original circuit. We found from original circuit, that is 22.857, and we found from Thevenin's theorem, or solving by Thevenin's theorem, exactly 22.857 milliamps. That's very simple. In computation, you can use complex networks in solving this problem, what is the basic utility? Basic utility is that as a student, you want to learn, you want to earn knowledge from the practical problems. Now during this solving the problems by your own, you can check whether it is correct or not by using this software simulation. Next we are gonna use Norton's theorem for solving the same problem here shown. By using Norton's theorem, we will solve the same problem, and that is a series arm impedance of 100 ohms and 180 ohms, and shunt arm impedance of 150 ohms. Now the current will remain the same through this. Current will remain the same through this, that is it is 22.857 as depicted earlier in the Thevenin's theorem. Now what is the difference between Thevenin's theorem and Norton's theorem? The basic difference is that during calculating the open circuit voltage in case of Thevenin's theorem, we would have shorted this path, that is the load path, removed the 75 ohms resistance and shorted this path. But instead of we would have open this path, but instead of opening this path and measuring the open circuit voltage, we will short this path and measure the short circuit current, that is 30 milliampere here. It is in the current mode, not in the voltage mode. In Thevenin's theorem it was in the voltage mode for measuring the open circuit voltage. And as you can see here, finding the short circuit current. I repeat, making the 75 ohms open and shorting this path, we can measure the short circuit current. Then what is this? This is finding Norton's equivalent resistance, the same as depicted earlier, that is 2240 ohms. And next we need to design the Norton's equivalent just like the Thevenin's equivalent, but instead of writing the VTH found in Thevenin's theorem, we will connect the ISC, that is short circuit current or Norton's equivalent current source, 30 milliampere here, in parallel with the TH or Thevenin's equivalent or Norton's equivalent resistance 240 ohms in parallel with the resistance, and we can measure the current to be exactly 22.857. So solving the same problem using Thevenin's theorem and Norton's theorem is basically the same. You can use complex problems for solving these problems again and again, and learn how to solve complex problems by your own, by checking this, by making this simulation very effective. So that's all for today. See you next time.